much. And cheers, Dan. That was really good. Obviously, the difficulty here is trying to make sure we don't all say the same thing. So I appreciate that. My background is in looking particularly across things like the automotive sector, but looking at where are these things going to end up and what are the kind of methods that you would need in the face of a very adversarial situation and with evidence. So see if I can make it work from going downwards. So some of the questions that I thought you might want to look at, or we might want to look at: how's machine learning or AI different from your regular complex systems? What are you using machine learning? Where are you using this? What are your failure modes? And what's the standard type of evidence and type of evidence that you're going to require for your machine learning system? So I'll try and explore those as we go through. I thought you might like to actually start with this. This was a putative press article that was developed in association with a research institute in the UK and a subsidiary there that went with called Flint, for which we're very grateful. Which is essentially looking at what might it look like, in 2031 when you see accidents happening, when you see things that are actually based on these things. How would you have to give evidence? What would that mean? And therefore, where would you end up in relation to those? It looked at trust being removed in relation to those things, so it wasn't purely a technical thing in relation to that. The lobbying of various groups and things that happened in relation to that. So I won't give you too much time to read through all of this stuff, but just to say that these things are elements that we've looked at, and particularly we've looked at things like data extradition and things of that nature in relation to the models, on the basis that many of these things are actually not being done in the UK, not being done in one territory, and it's not clear how you get at those sorts of things. So we're talking about all of these things in terms of what have you actually got to achieve. And what we set out to do was to look at a methodology that was suitable to go to court, that actually people understood what they were doing. That is our general thing there. So those that you know me will see that in the bottom diagram we've actually moved on to doing ships and transport systems as well as automotive as part of the analysis that we do in relation to this. And I'll move on to the next one that goes in relation to that. So the idea that we had there was that when you're talking about your machine learning AI system, it basically is something that is part of a system that must give resilience in relation to that. And the element in the middle there is actually an example of a real-time attack against or real-time poisoning attack against an AI machine or a machine learning component that was actually operating on a sensor in a braking system. So the ability to break that in such a way that people were not able to rely on its safety components or any of those sorts of things was the question that we were asking. So how do you counter that? What do you need to look at to be able to do that kind of stuff in order to get the kind of certainty that Mike asked me to talk about as part of this thing here? And the reason for that, because actually this is where you're going to end up. You've got key cyber risks. You've got elements that will be tested in criminal law. You've got things that will be tested in civil law, and there'll be fact-finding processes. So these are things where it will actually matter how you're doing this. Or to put it another way, in one way or another nowadays, it's starting to matter what you do. So you're either writing contracts, if you're a chip manufacturer, for instance, to explain why it's nothing to do with you and you shouldn't have used it, or you're writing contracts that are actually allowing you to, expecting to be using those sorts of things. And increasingly, organisations are legislating there, so they're legislating. You've seen the EU regulation starting to come out in relation to. So these were the principles that we looked at. So for a standard system, and started to look at, do they also apply to machine learning and AI? And the point about this is isn't some magic thing that is completely different in that sense. You've still got the one-bit variations. That is the basis of. For instance, that is the basis of the types of poisoning attacks that you're looking at. You're looking at bit variations having huge differences in relation to these things. So it's not a situation here where you're actually able to do things. The modelling and things that go in relation to these things, it's not something that's actually very easy to get a conclusion out of these sets of things. And it was quite clear that we had conflicting objectives in the systems that we were looking at, where we had objectives of privacy and safety and business value, for instance, but we also had many others. that aspect of being able to generate value out of data was a really important element that went with that. And our technical solutions needed to be giving the evidence to support these sorts of things. Now, many people have spoken to me about why simulation is the answer to this, and I certainly believe that simulation is a really good thing. I would not choose to drive a vehicle from London to Edinburgh without first going through simulation to try and make sure that it was okay, I guess, because the physical part is only able to get a restricted part of what you're actually looking at. But the really important element that comes out of that is that the cyber part of this is a much greater element. It is all the areas that you're not looking at. So it's effectively, it's an infinite space that you have in relation to that, that sits on the side. I know some of my academic partners argue about whether that's actually technically infinite or just in practice infinite, but it's a very big space compared to what you're actually able to do with simulation. So when you're looking for evidence in relation to these things, you're not looking for evidence based on the fact I've tested this little bit here, because when I come to attack it, it will be easily possible to do so. And we concluded this when we were looking at some of the braking systems. We had difficulties about who owned the sensor data. And as I said, that machine learning attack actually came out of poisoning the data there. We've done LiDAR attacks, which were designed by actually flashing lights into the LiDAR system. And the point about that is we started to discover that machine learning was being used in lots of different places and in lots of different contexts. So in particular here, I've done some circles around where some of these sorts of things may be. On the vehicle there, you may be looking at sensors. You may be looking at algorithms that are actually part of a complex algorithm that's trying to put things together in order to work out how you should behave if you're looking at autonomous vehicles. In your monitoring and adjusting of things, you may be looking at things where you're actually looking at how do you put things together. The candidate cases, when you're looking at simulations, that may be driven by AI, or you may have AI at the other end that's actually looking at how do you counter things. The AI model training that actually goes with simulation itself is a problem in relation to, or is a separate area there. And what you start to see there is machine learning and AI itself are being used at various different levels in different ways to try and achieve different objectives. So it's not that I have a single thing here that I'm doing and it's got an AI system on it. The different elements here are amenable to being broken in different ways by an attacker. And you need to recognize that when you look to try and put the evidence together. And that was why when we came to looking at what was the methodology we were looking at for these things, we suggested that you should move forward to a situation here where you look at how many engineered differences, things of this nature, how many updates do you have, and what is your ability to do this, to actually calculate the probabilities. And this comes to the failure modes. I have found it incredibly difficult on a digital system to put together the calculations in the face of a cyber attack for what does the failure modes look like. We have not been able to do the required probabilities that you would, for instance, require of an ALARP in order to be able to take that to court. And when I lace into that the sort of things that you're looking at for machine learning, it is much more difficult to understand what the failure mode of this might be compared to a normal digital system. We don't understand it's based on data that's really complex, and we like the outcome, but we don't necessarily understand exactly how you got to that outcome. And that aspect around it means that we understand less well than we would normally expect to what the failure modes on these things are. And increasingly, if you're looking for certainty and you're looking for assurance around your machine learning systems, then that ability to be able to determine that is going to be an appropriate and important element. That ability to numericize those things is going to be the sort of things that people in the regulatory community, people in the legal community, people in the insurance community are going to expect from you, whatever your business might be. So we would suggest in relation to that, that if you can't manage to put those numbers together, and we have yet to find a way by which you can put those numbers together effectively, the strategy has to be to manage the harm that you can do with these systems and to create the diversity. Do not create a single pandemic situation. Create a situation where you've got enough variability around these sorts of things. And that needs to be an absolute objective if you want to do certainty in your AI systems. To put this another way, when we were looking at automotive, and we were looking at how we put these things together, but it's applicable to many other sectors. It turned out that the human being was an incredibly important part of achieving the diversity that these systems required. Replacing that with a machine learning or an AI system that systematically operates in a pseudo-intelligent way but does everything the same is actually removing that element of diversity that the human being was responsible for bringing. And as engineers, if you want to have a way of actually documenting this, if you want to have a way of doing this, we recommend that you must find a way of putting that diversity back into your systems. So we recommend that you do this thing based on understanding these six arguments, or the 3 principles that we had on the previous page, and these 6 arguments in relation to that, how you will be able to do these things if you're going to be able to put together a proper system in relation to this. And the arguments in relation to this, stop pretending, so don't pretend that we know how to do these things. The advantages that you get out of AI and machine learning are huge. They are different at various different levels. So the advantages that ARM discuss when they're talking about how they can speed silicon to market by identifying the areas that they need to test. The advantages that you get on a sensor when actually you're looking at augmenting the capabilities of the raw silicon in order to be able to get the things that you need out of it. The advantages you get into an autonomous vehicle when you actually put these things together. These are all major and significant advantages that you get out of these systems. And I therefore am not in any way advocating that you should rein back and should not look at using these systems. But you should understand we are not going to be in a position, at least in the foreseeable future, to be in a situation where we're going to be able to analyze these and to remove the risk. And it is often the case that the failure mode is actually going to turn out to be the most important thing. Where do you want to go back to in the event that it doesn't work? And understanding what other people in your supply chain have done around that will be an increasingly important part of this. So the other things that I'd like to mention at the bottom there is the inability to actually scale the sorts of things that you're looking at. So one of the interesting elements that we looked on that automated tool chain that went with there is no way that software takes responsibility for things. So very often we've now got monitoring and analysis being done by software, and particularly software augmented by AI and machine learning, particularly when you're looking at cyber attacks. The important thing against that is how does that actually fit with your obligations to be able to say something? Ultimately, people take responsibility, companies take responsibility, software does not. And therefore, one of the questions for you is how are you going to be able to trust, or to what extent do you want to be able to trust the software that is doing that and the AI system that is doing that for you? Because you will need to map that to your organizations for what you're trying to do. And finally, we want to take advantage of tools. So this isn't a question that we're suggesting you don't do these things. Tools based on AI are increasingly emerging. So the systems that we're looking at have got AI in, but the tools themselves that are analysing this are actually based on AI themselves. That we think is a really important emergent property that you have at the moment, but I think that is actually something you must consider how you will be prepared to take that risk going forward. And I guess that's probably taken my time there, Mike.
5 minutes for questions, if we do have any. Let's see if we've got any questions.
I could pose a question.
Yeah, go ahead.
You talked about certainty and the difficulty in quantifying it, Peter. Have you looked at Bayesian methods for these things? Because that is sort of the field of quantifying uncertainty.
Yes, so we have looked at those, and we were able to quantify, and that I guess that was the difference that we. So firstly, what we meant by trying to quantify that at different with machine learning being used in different areas and different parts of the supply chain was the techniques appeared to be different. It was often a situation where the situation itself was too complex for us to be able to use the techniques effectively, and it just shuffled the problem down the road on what we were actually trying to do.
Interesting, thank you.
And Peter, there is one in the chat actually. So it's from Samir. He's asking if you make a distinction between the word complex and complicated. I think the bigger question is, do you see complexity as a security challenge?
I see complexity as a security challenge. Inevitably, you get emergent properties on that sort of stuff. You're looking at emergent properties, but I see it as the challenge for our age, if you like. Whereas 20, 30 years ago, my concentration was always on doing things at the smallest possible scale in order to get certainty. Nowadays, the benefits we get are from joining lots of systems together, making sure that we use data effectively. The scale of things that we have there inevitably introduces the complexity, and the benefits we get from that are really huge. Or at least if we do it right, the benefits are really huge. So I see it as a challenge that we have to embrace, not a challenge that we can avoid from a security point of view.
Okay. Thanks. One last question is, you mentioned using tools there. I'm used to sort of in the safety arena, if you need to use a tool to demonstrate safety, then that tool has to be demonstrated to be safe as well. By using tools, you have to demonstrate they're secure, or
you have to understand what claims you're making about them. So,
okay.
So it's not necessarily the same standard. You're not looking at safety critical tools in relation to that. But you are looking at how these things fail, what they do in relation to that. I guess the idea there that we had was, I don't believe that you're going to be able to put together enough certainty out of your tools or out of the elements that you have that you can get, particularly in this area of AI and machine learning, that you will be able to get the level of certainty that people would normally expect. But you should therefore concentrate on how you're going to get enough diversity in things so that you don't get the catastrophic failures. And then I think you're more likely to be able to put together an acceptable outcome.
Okay, but thank you for your presentation and for answering the questions. Thanks, Peter. And again, we're still on time, so thank you very much. Thanks, Peter.
Thank you.
And